going to continue with 3.1. Let's do a slight recap of what we did last time. Last time towards the end we spoke about some derivative properties. So one of them was the constant factor property. This says if I want to differentiate a constant times a function, how do I differentiate it?
It's the value factor.
You can factor the constant out and differentiate the function. Right? So you have to differentiate a constant times a function, you can leave the constant alone, differentiate the function, and that will give you the answer. I don't think I justified that to you, but the reason is this. So if your y is like c f of x, then your y prime would be the limit as h approaches 0 of c f of x plus h minus c f of x all over h. That's a limit. We already know from our properties of limits that we can factor out constants, so I can take that constant and put it out in front. And so that guy now is my just derivative of f. So I realized the derivative of a constant times a function is just a constant times the derivative of a function. Another property we had was the sum property. We know that the derivative of a sum of functions, how did we find that? It's really just the sum of the derivatives. So if I have a sum of functions being added together or subtracted, I can just differentiate each component and then add them together, and that would be the answer. And you might ask why. Like, no, I didn't ask why, but if you define a function to be a sum of functions and then you do the limit definition of the derivative, it turns out that the first guy would be you replace all x's with x plus h. But then you can kind of separate the fraction, right? We know we can split fractions across the numerator. So I can combine the f of x plus h minus f of x, put it right beside it, put that over h, plus take the g of x plus h, put minus g of x, put that over h, and take the limit as a whole. Right, that's me just splitting up a fraction, which we know we can do. This guy here is just the derivative of f. That guy here is the derivative of g. Limits distribute across sums, therefore the limit of the sum is just the sum of the limits, and I end up with f prime plus g. Right? So that's why that guy works. We really were using the limit definition. And those are the only two properties I gave you, and you might have wondered, why didn't I give you more? Why didn't I give you about the product of two functions? It turns out it's not as straightforward as this. If I have one function multiplied by another function, I can't just take the derivative by taking each piece. We'll talk about that later today. I also mentioned the derivative of a very important function. We looked at the derivative of e to the x, which was c to the x. It's the only non-zero function that is its own derivative is the exponential function, which makes it very useful for calculus, especially if we're dealing with exponential functions. Did I tell you about the chain rule?
Yeah, a little.
Okay, so I probably told you a little bit. So, okay. I just probably gave you the definition of one example.
Yep.
So the chain rule, this was a rule that told you how to differentiate composite functions. So this is like you're differentiating one function with another function plugged inside of it. And so that was, do you remember? Derivative of the outside, multiplied, not plus, it's multiplied by the derivative of the inside. And you leave the inside intact. So these are very important rules. These guys you should have memorized. I'm going to want to generalize this rule a little bit for you using the chain rule. Let's say I don't just have e to the x, I have e to something else. find y prime if my y is equal to, say, it's e to some other function, like g of x. How would you find that derivative?
E to the g of x.
Is it? Not quite. The derivative of e to the x is e to the x.
What's g?
But we have a chain rule. So now instead of x, I had a function plugged in to replace
G of x.
x.
Is g of x.
G of x is any function. So how do you find the derivative?
Can you bring out the g of x in front of the e? I think. Is that how it goes? No.
Find the
I'm
derivative.
thinking of something
Isn't it
else.
just chain rule?
Use the chain rule, but how? I want to know how would you apply the chain rule? Yep.
Well, you would take the derivative of g of x and put it on the front of the equation. Right,
Okay.
while maintaining e to g of x, and then take the derivative of e.
You went too far. What do you think?
Isn't it e to the g of x times g prime of x?
That would be it, based on the chain rule. So let's look at what the chain rules say, make sure we understand it. It says you take the derivative of the outside function. The outer function here is e to the x, right? It's kind of like if you had f of x equals e to the x, and your g of x is just g of x, and that guy gets plugged on the inside of this one. So your exponential is the outer function. So then you want to differentiate the outer function, but we have a rule to differentiate the outer function. It literally becomes itself. The derivative of that is itself. But because it's not just x, there's an inner function, I have to now multiply by the derivative of the inner function. So that would be the derivative of e to the some random function. In other words, I like to express this in a slightly different notation. That is, the derivative of e to the u, where u represents any function, is u prime e to the u. That is a very important rule, and this follows by the chain rule. Right? And it turns out that every basic derivative rule I give you, you can generalize it to use the chain rule. So anything that I give you a rule with just x in it, it turns out you can generalize it to include things that like not just x. So for example, if I had my y is equal to e raised to the x squared, that would mean my y prime would be equal to what?
E to the x squared times 2x.
Right, now x squared we already know how to differentiate that using the limit definition, and we'll look at another way later. But we know that its derivative is 2x. So the derivative of e to the x squared would be 2x e to the x squared. Let's figure out how to differentiate a different kind of function. Let's look at the natural log of x. How would you differentiate that? Does anyone know what the answer is? Yeah?
Isn't it 1 over x?
It's 1 over x, right? So that's something you're going to have memorized, but let's actually justify that a little bit. So set my function g of x to be ln x. My goal is now to figure out what is g prime. I'm not going to use the limit definition, even though technically we could. Here's what I'm going to do. Because I don't know how to deal with ln x, in theory at the moment we don't know how to do it, I want to get rid of the ln, so I won't have to deal with it. How could I do that? How do I get rid of an ln if I have an equation?
Raise it to e.
Raise both sides to the e. Now what that's going to happen is my right side now will just become x, and my left side will become e to the g of x. Now what I want to do is I want to differentiate both sides. Because if this is equal to that, then the slope of this is equal to the slope of that. They're the same. How do I differentiate this?
So we just did.
We literally just did that. That's g prime of x times e to the g of x. derivative of x?
One.
It's 1. We prove that using the limit definition. I'll give you another way to prove that pretty soon. But also you can realize that the slope of the function y equals x is just x equals 1, y equals mx plus b. So that's the derivative here. And so now g prime is what I want to figure out. So let's solve for it. This is e to the g of x. E to the x is never 0, so I know I can divide both sides by that. So this would mean that g prime of x is 1 divided by e to the g of x. But what is e to the g of x?
G prime of x
So that's
times-
where it cancels, but.
No, e to the g of x. What is that?
G prime of x times e to the g of x.
That's the derivative of e to the g of
This
x.
Oh,
It's just x. We have it here.
Oh.
E to the g of x is x. In this situation, if I assume my g of x is ln, then e to the g of x will just be x. And so then I get g prime is 1 over x. In other words, this tells me, you guys are imagining something that's not even there. No, it's right here. This tells me that the derivative of ln of x is 1 over x. And this is just a rule we know now. This is a very important rule, just like the other rules. We're going to have a bunch. By the time we finish with section chapter 3, we're going to have a bunch of rules at our disposal to differentiate a multitude of functions. And again, we can generalize this using the chain rule. I don't expect you to know the proof, even though the technique I use to prove it is an important technique. We'll actually cover it in a future section. But I do expect you to know the rule. Like, this is just something you should know now. Derivative of ln x is 1 over x. So again, by the chain rule, we want to generalize this. What if I don't just have e to the x? What if I don't just have ln x? What if I have something else? The derivative of ln u, where u can be any function, is going to be the derivative of the outside, which I know is just 1 over that thing, multiplied by the derivative of the inside. So that means the derivative of ln u is u prime over u. So in general, to differentiate the log of something, the ln of something, you just take the derivative of the thing divided by the thing itself. That is now a rule. Let me give you a simple example before moving on. So what if I wanted to differentiate ln of x squared plus x? How would you do that?
2x plus 1 over what's in parentheses.
So you put the thing that's inside the ln on the bottom. On the top, you put the derivative of the thing. So it's the derivative thing over the thing itself. Individually, we know how to deal with this, and we know that the derivative of a sum is just the sum of the derivatives, so I'm just going to differentiate each of these one at a time and put them here. Derivative of x squared is 2x plus derivative of x is 1. So that ends up being the derivative. So the slope of this function is that function. I'm going to derive another rule for you now. A very important rule. It's called the power rule. It's going to be the guy that helps us differentiate polynomials and anything that sort of looks like a polynomial. Anytime we have x to a constant power. So let n be a constant. Find f prime if f of x equals x to the n. Right? We're going to differentiate an expression that looks like x to the n. Now the limit definition has its limitations here because if your n isn't an integer, then you won't know how to expand the parentheses. So let's do this a little more general. So f of x equals x to the n. Here's how we're going to do it. I actually don't know how to deal with x to a power in general. Right? We know for when the power is 1 and when the power is 2, sure, because we proved that. But this could literally be anything. Radical 2. How do you deal with that? We don't know. So the powers is kind of troubling for us. So I want to rewrite this in a way that I don't have to deal with a power. Do we know how to deal with that? What would you use? Yeah?
Bring the n out in front and then leave it as an exponent minus 1.
You're telling me the answer. We're not there yet. How would I get out of a situation where I have a power and I don't want the power? I don't want to have to deal with the powers. What do we use? Yeah?
A log.
A log, right? I mean, I could just tell you the rule, but I'm really teaching you important lessons here, because in the future we're going to have ugly looking functions where you're going to kind of have to know how to deal with them in certain situations. If you have a power that you don't like, use a log to get rid of it. If you have an exponential that you don't like, if you have an ln that you don't like because it's complicated, use an exponential to get rid of it. This is a lesson that you should know. So here's a power. I don't know how to deal with the power, so what I'm going to do is I'm going to log both sides. Now this allows me to take the power and bring it down in front. So I have ln of f of x equals that. And now again, I'm going to differentiate both sides. What's the derivative of ln of f of x? Yeah?
A question. How do you know it's natural log?
Because I choose to use natural log.
Oh.
Remember, for calculus, e is the most convenient base. If I'm taking a log and no one tells me which I have to take, it's automatically going to be ln. What's the derivative of this?
F prime of x over f of x.
Right, the derivative thing over the thing itself. So this is going to be f prime of x divided by f of x. What is the derivative of where? Yeah, what's the derivative of this?
1 over x.
Well, there's the n, but the constant factor rule tells me that the n just stays by there, and then I differentiate ln x, so we just derived what the derivative of ln x was. That's 1 over x. So in other words, let me rewrite that. We now have f prime over f is equal to n times n over x. So in other words, if I solve for my f prime of x, this is just n divided by x times f of x. What is f of x?
X to the n.
Was x to the n. Now the laws of exponents take effect. This is x to the n divided by x to the 1, so overall it becomes x to the n minus 1. That gives us the power rule. So that tells us no matter what the power is, that is how you would differentiate x to the n. i.e., the derivative of x to a constant power is nx to the n minus 1. Very, very important rule because it helps us differentiate very, very important functions like polynomials. This is called the power rule. For derivatives. You don't need to know how to derive it, even though, again, this technique is something that we will be using in the future. It's called log differentiation. There's an entire section in our textbook on that, so we'll talk about that later. But knowing this is very important. Knowing that to differentiate x to the n, the derivative is going to be nx to the n minus 1. Let's do a few examples. What I want to do first is I want to do all the examples we kind of already know the answer to, that we proved using the limit definition. It took a while, but we're going to realize now with the power rule we can actually rederive all these rules very easily. So let's say I have the derivative of x. How do I define that? Derive that? Well, I realize that this is x to the 1, and so by following the power rule, this would be just become 1 times x to the 1 minus 1. That's just 1 times x to the 0, which is 1. So we know that the derivative of x is 1. Right? We knew that before we did it with the limit definition. It took a while, but now with the power rule, it's very short. I can also show that the derivative of x squared, well, in this case, my n is 2. I'm going to take that 2, bring it down in front, and then take 2 minus 1. And so So that gives you 2x. So the derivative of x squared is 2x. Again, we already knew that, but we can literally do it in one step now. Right? This is the power of the power rule. Right? Power rule for derivatives. I already put 4 derivatives. Because we're going to do something called antiderivatives and integrals, and it has its own power rule. So this is the power rule for derivatives. Something you should know. You should know it by name. So if I write it on a quiz, what is the power rule? You should know that equation. Just like how I can say, what is the definition of a derivative? You know how to write down that limit definition. You should know how to write down all these rules I'm telling you. The chain rule, the power rule. What else could we derive using the limit definition? I think we also looked at how to derive 1 over x. You can use the power rule here as well. The trick is to use your laws of exponents. So again, all the algebra stuff I told you at the beginning of the course is going to be applying here. So if you see something like that, the trick here is to just rewrite it as x to the minus 1. And now it's just like the power rule. You have x to a constant power. Your n is minus 1. So you take that minus 1, bring it down in front. It's x to the minus 1 minus 1 by the power rule. So that's minus x to the minus 2 is your answer. Or to make it look like our answer from before, minus 1 over x squared. We also looked at radical x, and that one was kind of annoying because we had to like multiply and divide by the conjugate. Turns out with the power rule, that's also not so bad, because I just rewrite this using the laws of exponents as x to the 1/2. So now that's x to the n. I can do the power rule. Bring the half down in front. A half minus 1. That's my derivative. So that is a half x to the minus half. In general, that answer is fine for me, but if you want to make it look like the answer we had before, just realize x to the minus half is just 1 over x to the half. X to the half is radical x. So I end up with 1 over 2 radical x. That was the form we had before. It's exactly the same. Right? With a lot less struggle. Right? So the power rule is very powerful. Right? There are a lot of things we can rewrite. Even if they don't look like that in the beginning, there are a lot of things we can rewrite to look like x to a power. So not only does this work on polynomials, it works on radicals, it works on all sorts of things. We also looked at the derivative of a constant. The trick here was to realize that this one is a little bit more sophisticated. You kind of put something there that wasn't really there. Just realize that this is c is c times 1. 1 I can think of as x to the 0. Applying the power rule here. My constant says I bring a 0 down in front, x to the 0 minus 1, but that 0 sort of kills everything. So the answer is 0. So yeah, we just derived all the rules we knew so far in the time it took to derive one of them using the limit definition, using the power rule. So it's a very important rule. As well as you should be aware that we can combine the power rule with the properties of derivatives and nothing else would change. So for example, find y prime if, let's say my y is 3x cubed minus 7x squared plus 12x minus 1 over x cubed. So let's say that's my function. Now hopefully you can appreciate how annoying that would be using the limit definition, right? X plus h raised to the cube power, right? You'd spend a long time pulling that out if you don't remember. So that would be like x cubed plus 3x squared plus 3x plus 1. And then you're going to have that in a denominator. So then you're going to have this insane looking complex fraction. It's not going to be a fun time doing the limit definition. But it turns out that I can actually do this pretty easily using the power rule. So because, one, look at all these functions. They all look like x to the n. What about this guy? X to the negative 3. I can actually rewrite that guy as x to the minus 3. And now they literally all look like x to the n. I know that the derivative of a sum is just the sum of the derivatives, so I just can focus on one of these at a time. That's not a problem. And I also know that the derivative of a constant times a function is just a constant times the derivative of the function. So these numbers in front are also not a problem. So if I go to y prime, to differentiate this guy, leave the 3 alone, and differentiate this using the rule that applies, which in this case is the power rule. So that would be 3x squared, right? Bring the 3 down, subtract 1 from the power. Minus, you move on to the next guy. This is 7 times, now you differentiate x squared, according to the power rule, you bring the 2 down, subtract 1 from the power, 2 minus 1 is 1. Plus, the 12 stays, times, to differentiate x, use the power rule. There's a power of 1 here, bring the 1 down, and you have x to the 1 minus 1, which is 0. Again, here do the power rule, right? So the minus 1 stays, bring the negative 3 down, and that's x to the minus 3 minus 1. And that's the derivative. Now I can just kind of rewrite to simplify things a little bit. 3 times 3 is 9. 7 times 2 is 14. Plus 12. Plus 3x to the minus 4. And that would be the derivative. So if this is my function, that gives you my slope. Clearly a lot easier than it would have been with the limit definition. So that's called the power rule. Very important rule. Let's do some other rules. So I told you about that property of the sum, right, which we actually used here, right? Because the derivative of a sum is just the sum of the derivatives. Let's look at another important operation, multiplication. What if I have a product of functions? Is the derivative of a product just the product of the derivatives? Right? If I wanted to differentiate f times g, is that f prime times g prime? It turns out that the answer is no. When it comes to multiplication and division, derivatives, the limit definition actually doesn't work out that nicely. You can see this for yourself, right? Let's say the derivative of x squared. We know what that is, right? What is that? That's 2x. Okay. Let's say I rewrote x squared to be x times x, right? And I want to differentiate that. If I differentiated each piece, what would have happened? Derivative of x is 1. Times derivative of x is 1. I would get the answer 1, which I know is not the answer. So obviously this rule does not work. So what rule works? How do we differentiate a product? I'm going to show you. I just thought of another way to figure out the product, to do the product rule. Okay. So let y equals the product. F of x times g of x. This is the standard proof I'm going to give you, but there's probably also a nice proof to do with logarithms, right? You just take the ln of a product, you split it into 2 logarithms, use the log derivative rules and rewrite stuff. But I'm going to give you the standard derivation. It's actually using the limit definition. So if you don't know what a derivative looks like, or how to deal with the functions, you can always go back to the limit definition. So this is going to be, replace all x's with x plus h, minus functions with x, all over h. And now we are going to actually try to simplify this limit into something nice. We're going to do a little trick here. We're going to sort of pull something out of nowhere, essentially. This is a technique that we do know from math, like when you're completing the square, this is sort of something you do, you kind of add and subtract something. We're going to do that here as well. So I'm going to add and subtract something convenient that allows me to rewrite this. I'm going to subtract f of x times g of x plus h, and add f of x times g of x plus h. So I'm really adding 0, I'm not changing the value of anything. But you'll see why this was a convenient thing to add and subtract. It's because I'm after a certain pattern. So I add and subtract this guy, I'm adding 0. What I'm going to do now is I want to split these fractions into 2 parts. So So in the first fraction, I would have essentially f of x plus h times g of x plus h minus f of x times g of x plus h all over h, plus in the second fraction, I would have f of x times g of x plus h minus f of x times g of x all over h. Let's put that fraction into two fractions. Now I'm going to want to simplify these fractions. How do you simplify a fraction? You factor. That's how you do it. Right? So I'm going to factor out, there's a common term here of g of x plus h. There's a common term in this one of f of x. Let's factor those two guys out and see what we have. So then what I would do here, I'm going to factor out the g of x plus h. So I have that. Plus, here I'm going to factor out the common f of x. So I'm going to put g of x plus h minus g of x over h. Recognize anything? I know the limit, though, limits do distribute across both sums and products, so I know the limit of a sum is the sum of the limits, so I can take the limit of this and the limit of that. I also know that the limit of a product is the product of the limit, so I can take the limit of this and the limit of that separately. What's the limit as h approaches 0 of this?
F of x.
Hmm?
F of x.
It's not f of x. What's the limit as h approaches 0 of f of x plus h minus f of x over h?
F prime of it.
It's f prime, that's the derivative. Times derivative of g of x plus h as h approaches 0, well that's just g of x, just plug in h equals 0. Plus, well that's just f of x, nothing to do there. What is the limit as h approaches 0 of g of x plus h minus g of x over h?
G prime.
That's g prime. So it turns out that's how you differentiate products. Differentiate one function, leave the other function alone, plus differentiate the first one, differentiate the second one, leave the first one. This gives us the product rule. This tells us that the derivative of one function times another function is f prime times g plus f times g prime. Differentiate one function at a time and add them together. Very important rule. This is called the product rule. So that's the product rule for derivatives. Or just the product rule. There's nothing called the product rule for antiderivatives. The analogous thing would be integration by parts, but that's the product. Let's do an example here. Let's say I wanted to differentiate x times e to the x. Notice here this is a multiplication of functions. I have one function which is x, another function which is e to the x, and I'm multiplying them together. How do I find the derivative?
Take the derivative of x multiplied by e to the x.
So I know I can just, in your mind's eye, just think of these guys as being called two different functions. You put the multiplication. And then you just apply the rule. You know you're going to write down f prime times g plus f times g prime. You just pretty much write them down. So what is f prime?
1.
That's just 1 times g, which is the original function, e to the x, plus
X.
f, which is the original function, times g prime.
E to the x.
Derivative of e to the x is e to the x. So this, the derivative of x e to the x is just e to the x times x e plus x e to the x. Or, which is not always necessary, but you could factor out a common e to the x, and that's that guy. There are cases where you want to factor, but sometimes you don't have to. Here, don't worry about it. So that's how you differentiate that function. That's using the product rule. Very important. Definitely have it memorized. I will ask you all these rules on the quiz. So I'll ask you about how you define a derivative using limits. What is the power rule? What is the product rule? What is the quotient rule, which is I'm going to tell you about now. Write down the chain rule. You should be able to write all these down and apply them.
So
Yeah.
derivative of e to the x is e to the x?
Yes, derivative of e to the x is e to the x. Okay, so the question might be, what about division? So if I have one function divided by another function, what is the derivative of that? Can I just differentiate the top and divide by the derivative of the bottom? Turns out no. Right? Multiplication and division are linked very much. You can think of one as the other, in fact. So odds are if something doesn't work for multiplication, it's not going to work for division either. But here it clearly doesn't work. You can see it again. Let's say I use again the derivative of x squared as an illustration. We know that the answer should be 2x. However, let's say I rewrite x squared to be a fraction, something like x cubed over x. If I differentiate the top, what would I get? What's the derivative of x cubed?
3x squared.
3x squared. If I differentiate the bottom, what do I get?
1.
1. So this is telling me derivative of x squared is 3x squared. That obviously makes no sense. I know that 2x is the answer. Okay? So again, when it comes to divisions, you can't just differentiate each piece and stick it together. That's not the way to go. So what is the way to go? Let's derive it. And it turns out with the product rule and the chain rule, we actually don't need to go all the way to the limit definition here. We can do it on a slightly higher level. The trick is, if I have f of x divided by g of x, I could rewrite this as f of x times g of x to the minus 1. Right? Just using laws of exponents. So I can rewrite a division as a product. And now I'm just going to apply the product rule. Right? So the product rule says, differentiate this function, leave that function alone. Plus, you leave this function alone and differentiate this function. Now here's the question, how do you differentiate that function?
Bring down the negative 1.
Bring down the negative 1
And subtracting from the exponent.
to get minus 2. Is that it? Seems legit.
Multiply by the derivative of g.
You have to multiply by the derivative. Right? Because of the chain rule. It's not just x to the minus 1. There's an entire function plugged in for x, right? So this is actually a composite function here. So the chain rule actually applies. So I had to do the chain rule here. And by the way, this is not at all strange. There are many problems that you will have to do in this class where you're applying multiple rules at the same time. So you can't forget any one of them. There are times where while you're doing the product rule, you have to do a chain rule on the inside of it. That's not strange at all. Right? So yeah, I had to apply the chain rule here because that was actually a composite function. It wasn't just x to the minus 1. There's a whole function plugged in for x. And so now, let's rewrite this a little bit without the x's. So basically I have f prime plus times g to the minus 1 plus f times g prime times g to the minus 2. Alright, so that's what I have so far. Let's actually rewrite this to look a little nicer. So essentially I have f prime divided by g, because g to the minus 1 is just 1 over g. There's a minus here. And so I have minus f times g prime divided by g squared. Right, so the g to the minus 2, I moved down to the bottom, the minus sign came out in front here. So now I have two fractions, let's combine it into one common denominator. So I multiply by g over g. So this becomes f prime g over g squared minus fg prime over g squared. So I can combine this into one big fraction. So this is f prime times g minus f times g prime over g squared. In other words, the derivative of one function divided by another function is bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. Very important rule. This is called the quotient rule. Because quotient is another word for division. It's the result of a division. Yeah?
Well, we need to know the proofs of the rules, or just the
No.
rules?
You just need to know the rules. Right? So now this one is another thing that you're going to have to memorize, and there are many mnemonics for the quotient rule. So one was I literally say the phrase out in my head like I was just saying. The bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. A lot of students also have the mnemonic with low d high minus high d. I don't know if any of you ever heard of that. So it's like low d high minus high d low over low squared is another way students remember it, where they call the top function the high function and the bottom function the low function because it's lower. So like, oh, low d high minus high d low over low squared. And so that's the original function times the derivative of the top function minus the top function times derivative of the bottom function over the bottom squared. Right? But however you memorize it, you need to memorize it. It's called the quotient rule. Also be aware, note, order matters in the quotient rule. In the product rule, the order actually didn't matter. Whichever function you thought of as the f and the g, whether you put the f on the right and the g on the left, or the f on the left and the g on the right, it doesn't matter. Because you're adding them together. You can add things in any order. With a minus sign, though, it makes a difference who comes first, right? 2 minus 3 is not the same as 3 minus 2, right? So you'll literally get the negative of the answer you should get if you remember this in the wrong order. So the order matters in the quotient rule, so that's the first thing. So make sure you memorize that well. It has to be the derivative of the top times the bottom first. Then you subtract the top times the derivative of the bottom over the bottom square. Okay, so the order matters here because of that negative sign. Let's do a small example of the quotient rule. Say I had x divided by e to the x. How do we deal with that? Yeah?
E to the x minus x e to the x over e to the x squared.
Okay, so let's go through that carefully. The fx here, I'm going to call my f. The bottom, I'm going to call the g. And in this case, it matters who I call who if I'm plugging into this function. So the top is the f and the bottom is the g. And so now I know I want to do f prime times g minus f times g prime over g squared. So I know that's what I'm going to want to plug into. So you just plug them in one at a time, just like with composite functions in general. F prime is the derivative of this, which is 1. The g is just the original, e to the x, minus f, which is x, times g prime, derivative of e to the x, is e to the x, all over the bottom squared. So this is e to the x squared. And that would be your derivative. Of course, you can simplify a little bit here. So I can factor out a common e to the x. This is 1 minus x divided by e to the x squared. And cancel that. So this becomes 1 minus x over e to the x. So that's the quotient rule. So far now we know how to differentiate e to the x, ln x. We know the product rule, the quotient rule, the power rule, the sum difference rule. Oh, a couple things. I actually entered into another section. By the way, the product and quotient rule is section 3.3. Here's another thing I'd like you to note. The quotient rule can be slightly annoying because you can get really big things from the quotient rule. For example, on the review and on the first test, there was this massive thing that you had to simplify, this fraction. I don't remember what the fraction was, but there was, you know the one, the huge fraction. Okay, it turns out that fraction I obtained by doing the quotient rule on a function that was relatively simple, and that huge thing came out of it. Right, so applying the quotient rule, a lot of times the simplification can be annoying. So there are times when you don't want to apply the quotient rule. So let me just talk about that. So there are times when you might see a problem and it might look, it's a division, so you're like, you might just like, oh, let's use the quotient rule. But it's worth your time to relax and consider, do I really need to use the quotient rule? Because you can end up making a lot of mistakes and end up having to simplify things that you don't need to worry about. So the rule of thumb is not that bad. It's do not use if the numerator or the denominator is a constant. So quotient rule just becomes unnecessary in either of these cases. So essentially, if the numerator is a constant, what you would do is you'd rewrite and use the chain rule. If the denominator is a constant, that's even easier. Just leave it alone. You don't have to do anything. Just differentiate the top and leave the bottom alone. Let's illustrate. Let's say I wanted to differentiate. This is kind of something we've looked at before. So if you want to differentiate something like 1 over x squared, right? You could do the quotient rule here, and it would work out. But you wouldn't want to do that. It's just really overkill. Notice that here in this case the numerator is a number, it's just 1. So what I would do is I would just rewrite it. Rewrite this, I can rewrite that as x to the minus 2 instead, and just use the power rule. That's minus 2, x to the minus 2 minus 1, so that's minus 2, x to the minus 3. So that would be the derivative there. It can look a little bit more complicated even, so I could have something like this. 1 over the square root of x squared plus 1. It's another fraction. You might think, oh, it's a division, I should use the quotient rule. Quotient rule will be overkill in this case as well, because you can actually rewrite that as well. How could you rewrite that?
X squared plus 1 to the negative 1/2.
Storm is really picking up. I thought it would.
Maybe write this all down.
Right, that's x squared plus 1 to the minus 1/2. I can just rewrite that using the laws of exponents. And now I can apply, it would be the chain rule. It's not part of the power rule because it's not just x, there's a function plugged in for x. So whenever it's not just x, you have to use the chain rule. So you differentiate the outside, leave the inside alone. Then you multiply by the derivative of the inside. Derivative of x squared plus 1, derivative of x squared is 2x. Derivative of 1 is 0. So this becomes, the 2's can cancel. So I get minus x squared plus 1. Minus 1/2 minus 1 is minus 3/2 times x. Or if you want, you can write x over the square root of x squared plus 1 cubed. But that's fine. It's a lot nicer than using the quotient rule. One thing I see students often do with the quotient rule, when they apply it in these cases, is they forget while doing the quotient rule that the derivative of a constant is 0. So a lot of times what I'll see happen, right, it happens all the time. So I'm mentioning it's not like an unfounded concern here. I see it happen all the time. So forgetting that the derivative of a constant equals 0 while doing the quotient rule. So for example, let's say you wanted to use the quotient rule here. So what would you do? It's the bottom times the derivative of the top, which is a 0, minus the top times the derivative of the bottom, where you're going to have to apply the chain rule in the power. So that's going to be a half x squared plus 1 to the 1/2 minus 1, all over this guy squared. So in the first place, it already looks kind of messy. So if you're especially not up to scratch with the algebra, you'll probably make a mistake here. But the mistake that I often see is students often put the 1 back here. They often put a 1. That's a mistake. Right? Derivative of 1 is 0. Right? So they often do this and then they put the 1 here and they just keep the 1 for some reason. I don't know what's happening. I don't know why that happens exactly, but it's something I see all the time. Students forget in the quotient rule, while the numerator or denominator is a constant, they forget that the derivative of the constant is 0 and they keep just copying down the constant. So don't make that mistake. The derivative of the 1 is 0. Okay. So you could have gone with that, which in any way what would have happened is, oh, I need to multiply by 2x here. This first term would have gone away. You would now end up with this mess here, which you now have to simplify to that. So what's going to happen, this would still cancel. This you can bring down and that would give you the 3/2 power, but I feel like to go from this to that, like someone would make a lot of mistakes. Especially if you're in a test where you have 5 problems to do and this is one problem with 3 parts in it and this is one of the parts. Just don't kill yourself by doing this and risk making mistakes. Just rewrite it.
Wait, where does the 0 come from?
Huh?
What 0?
Derivative of 1.
1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1.
in the quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. But my point is, whenever the top is like a constant or something, students always forget that that should be a 0. Often forget that that should be a 0. So while it won't be wrong to use the quotient rule in a situation like this, it introduces room for errors that you don't want to have to make because you're rushing in an exam. Another example, let's say I wanted to differentiate x cubed plus x all over 3, or something similar. You can literally just ignore the denominator, just leave it alone. And then you can just differentiate the top. That's your answer. Right? There's really no reason to go through the quotient rule.
What rule is it that lets you leave the denominator?
I'm going to ask you that. That was my question. Why can I just leave the denominator? Yeah?
Because it's technically a constant of 1/3.
It's a constant factor of 1/3. In other words, if I see x, this plus this all over 3, it's exactly the same as me saying 1/3 times x cubed plus x. So the rule says I can just leave that alone and differentiate this. And then when I multiply through back by the 1/3, I end up just putting that through the denominator again. So if you see this, really just apply the constant factor rule, which basically how it ends up being applied here is literally just leave the denominator alone. So if the denominator is a constant, you just leave it alone, ignore it, and differentiate the top. It's not worth going through a whole quotient rule. It's pointless. And again, you might forget that, oh, your derivative of 3 should be a 1 and it should be a 0, and then it's a lot more hassle than it has to be. Okay? So if the numerator is a constant, just bring the denominator up, write it to the negative power, and do the chain rule. If the denominator is a constant, just leave it alone and differentiate the top. Right? Because the chain rule helps us in that situation, and the constant factor rule helps us in that situation. And they're both algebraically easier to apply. Okay. So I've told you about the fundamental derivative rules. So technically, you know everything about how to differentiate anything for the rest of the course. There are some situations, though, in which applying these rules might be tricky, and we'll deal with that as it comes. For example, like implicit differentiation is one of the feature sections. But for now, let's just do a bunch more examples just to sort of make sure we fully understand these rules. So I'll copy these all down. I don't know if you'll get through all of them in 15 minutes, but so differentiate all these functions. I mentioned that things would be going really fast. It turns out that once we get away with these shortcuts and we don't have to do limit definition, we actually get through a lot of problems in relatively a short amount of time. We don't have to be computing f of x plus h minus f of x over h. We won't do all of these, but we'll finish them by the beginning of next class. Okay, so let's start with the first one. Or I'll wait till you guys talk. So even if I don't finish them today, you can try them at home. You know everything to do all these problems. You can try them at home as extra practice for the quiz. And I should just mention here, we skipped 3.2, right? So the homework for 3.1, 3.3, 3.4 due next Friday. So what date is that? The 9th?
Yeah.
March 9th. Alright, so this is where we figured out the sum rule and the constant factor rule and the power rule was in this section. The product and the quotient was in this section and the chain rule was in this section. So we've covered all of them. I think it flows nicer when I just run one into the other and not have to worry about designating the sections. So there's also one more example I want to do in 3.1, so I don't want to set the homework due for 3.1 yet. It's going to be a word problem where we kind of apply derivatives to a motion problem. So after these, we'll do one of those, and then we'll move on to section 3.5, which is implicit differentiation. Okay, x cubed e to the x, how do we differentiate?
3x.
What rule are you using? So you use the product rule. Notice that these are two functions being multiplied by each other, so we have to apply the product rule. So you differentiate the first one, you get 3x squared e to the x plus so that's the derivative. What about y is equal to the radical of x e to the x? Product rule again. That's one function times another. How do you differentiate this guy?
1 over gx.
Well, you have it memorized. If you didn't, you could write this as x to the half and do the power rule. So it would be a half x to the minus a half. But if you have that memorized as 1 over 2 radical x, that's fine. So it's that times e to the x. Then what?
Plus a square root of x. E to the x.
That's the product rule. Yeah, let's just leave it at those things. Even though we probably have more time.
I'm gonna take picture of you. Thank you.
What number were you up to?
I was doing number 11. Or I was
Yeah, but
picture now.
did you copy them down or
I
no?
did now. On my phone.
Did I erase anything that anyone was copying?
No.
So we're okay? Okay. Can you get rid of this? Right here? Okay. How do you differentiate that? Product rule again, because one function times another function. So what do you get? Oh, derivative of x is 1 over x. So that's 3x squared over x, so it's just 3x. I could write this as 6x ln x plus 3x. How would you do this one? What's so funny? I would actually do it another way. There are going to be cases like this. What is another way?
Rewrite it and combine the
You could rewrite this, right?
things. It's x
This is
times
just x to the half,
1/2.
x to the 1. So this is really just a fancy way of writing x to the 3 halves. And then I can just use the power rule. I don't need the product rule. 3 over 2 x to the 1 over 2. Right, so could use product rule. But overkill. The idea being is that whenever you have these sophisticated rules that you're using, sometimes you want to see, can I avoid using them? So yes, there's the quotient rule, yes it always works, but you can always look, can I avoid the quotient rule? Can I avoid the product rule? A lot of times there are situations in which, and this is a very simple situation, but they can be worse, where it's much easier to just use algebra to simplify the thing before worrying about the calculus of the situation. Yeah.
Can you explain that one more time?
Which-
Like why it's x to the 3 halves?
Oh, I use the laws of exponents. This is x times x to the 1/2. So this is x to the 1 times x to the 1/2, you add the powers.
Oh,
And so that's 3 halves. So this is really just that, and I can just use the power. I didn't need the product. Try this one, x plus 1 over x plus 2. You can do the quotient rule. I'm not sure if you need the chain rule. So you'd say the top is f, the bottom you call g. So what do we have? Is the bottom times derivative of the top, so derivative of f, which is?
I'm not going outside.
It's a little video.
I guess that's a sign.
Alright.
We'll pick up next time. I have to fix that window.